Oh, good night for some people, as they're reminding me in the chat. I am tuning in from Michigan in the US. If you want to drop in the chat, I love all the good mornings, but maybe let us know, how long has it been since you've taken trigonometry? Just to let us know. Some people it's probably quite recent, and others it's probably been a few years. About 20 years for someone, 3 years for many. All right. Well, we're up to 500 participants. We will let people keep joining. Just to introduce myself quickly, hi everyone, my name's Rachel. I'm the program director for Qubit by Qubit, the Coding School's quantum computing initiative, putting on this Introduction to Quantum Computing course. And as folks know, we kick off with our first official lecture tomorrow from 2 to 4 p.m. Eastern Time. And right after this, we will have a welcome panel with our teaching assistants, including Rahul and Corbin and several other people from the team. So please plan to stick around after for that. It should be a really fun conversation about how our academic team found their journey to quantum computing. But in the meantime, thanks for being with us this morning, this evening, whatever it is for you in your part of the world. Corbin and Rahul have put together a really, really excellent trigonometry review. As we've mentioned several times at this point, Trig is a really important prerequisite for many of the topics that we'll cover, especially with the math concepts in this first semester. So they have taken out time on their Saturdays to do a supplemental course for those who want to polish up their skills, refresh sine, cosine, tangent ahead of the math lectures this week. So just a quick introduction. Corbin is a fourth-year software engineering student and Howe National Scholar at the University of Waterloo. I'll let him introduce himself a little bit more, but he is incredible. And then we have Rahul, who's a postdoctoral researcher at the Quantum Materials Center at the University of Maryland. So excellent leaders in the field, and I'll turn it over to them so they can talk us through. We'll be here until 11:30, so for an hour and a half, and we'll take a 10-minute break in the middle. All right, Corbin, over to you.
Excellent. Thank you, Rachel, and good morning, everyone. I'll continue a very quick introduction of myself before we get started with this presentation. As mentioned, I'm a fourth-year student at the University of Waterloo. I'm currently doing an internship doing quantum computing research at a startup called Qubit in Boston. I was actually introduced to quantum computing back in high school as part of sort of like a summer camp. So I feel like I can sympathize with a lot of you just as far as there's a lot of new math floating around in this field, but it is a very exciting field. And I think all of us on the teaching team are really looking forward to being able to bring this to you over the next sort of year of this course. So we'll get started with this trig review. My name is Corbin. Rahul will be presenting sort of the second half of this, so he'll do an introduction a little bit later on. And we'll just start off with a quick overview of the topics that we'll cover today, so you have some idea of what's coming up. So first of all, we're going to talk about the bread and butter of trigonometry, sine, cos, and tan. Now, even if you are familiar with these in the context of sort of high school math classes, we're going to take a little bit of a different spin on this and introduce it in a way that really emphasizes how these topics are used within quantum computing. Second, we'll talk about radians as a measure of angles and how they compare to degrees. It's a very, very similar idea to degrees. So part of this discussion will also be why we bother introducing this new thing called radians anyway. Third up, we'll talk about some special angles that come up often in quantum computing. We will play around with them and show them in a very visual way to give you some intuition for what these things are. And then the last part of my section will be just talking about some useful trig identities. So these are just equations that will always hold and turn out to be very useful, again, within quantum computing. So the theme here is we are not doing a full review of everything within trigonometry. but we are going to be covering the things that are most pertinent to quantum computing in a hopefully very visual way to give you some intuition leading into the rest of the course. Then we'll take our 10-minute break before we launch into Rahul's portion on Signland, which is sort of applications and explorations of all the things that I talk about in the first half. He'll talk about different coordinate systems. Polar and spherical are two very important ones that are used a lot in quantum computing. So we're going to cover those bright and early. And then second, he's going to talk about waves. If you've ever heard people talk about quantum computing, especially in pop culture and science, you might have heard the term wave function. We're going to start getting into what some of these things are and why they're important for quantum computing this morning. Some simple objectives for this review. Biggest one is just we want you to feel comfortable with the trig functions, sine, cos, and tan. So hopefully you get that out of this morning's lecture. We want you to be able to use the identities talked about to simplify and convert expressions. So as we get into more of the mathematical content later in the course, you can follow those derivations a little bit easier. Third, we want you to have some familiarity with all the different parts of Signland that Rahul is going to discuss later on, from coordinate systems to wave functions. And then finally, we want you to have fun. That's kind of an overarching theme of this course, because I think on behalf of all of the teaching staff, we all think quantum computing is very beautiful and exciting for a whole host of reasons. I'm sure you'll hear more about that, but this is always going to be a goal for us. So let's start things off, sine, cos, and tan. Now, you might have noticed on the opening slide here, I had a little quote that said, trigonometry is the worst name in mathematics. And the reason I say that is that when we talk about trig within quantum computing, we normally like to think of it with respect to circles. Now, a lot of the times, as I'm sure some of you are familiar, trigonometry is introduced with triangles, right angle triangles, and angles, and all that kind of stuff. We are purposefully going to try to stay away from that, because in quantum computing, whenever we use trig, we are talking about circles. And so it's going to be fairly natural to start off with something called the unit circle. Now, the unit circle is just a object that we define, and I'm going to throw the definition up here on the slide. There's three important things. Number one, clearly the unit circle is a circle. Number two, it's centered at the origin. And number three, it has a radius of 1. So I'm going to go ahead and give my best attempt at a freehand circle over here. Just like this. So that kind of covers off point number one. We'll just call that a circle. As I mentioned, it's centered at the origin. So I've already kind of done that here. The origin is just the point at the middle, 0, 0. And the final point is that our unit circle has a radius of 1. And so that means if we go from the origin to any point on the outside of the circle, that's going to have distance 1. So just as an example here, if I start at the origin and go straight out along the x-axis to get to this point, that's going to have an x-coordinate of 1, because we know that the distance, the radius of this circle is 1. The y-coordinate right there is 0. We could do a similar thing if we go straight up along the y-axis and getting to this point here. Here, the y-coordinate is 1, again, because this is the unit circle and we haven't gone anywhere in the x direction. Same deal if we go out toward the left on the x-axis. Again, unit circle, distance of 1, this time in the negative direction. So we get -1, 0. And on the bottom here, same deal, but in the y direction. We don't go anywhere in x, and we go a distance of -1 in the y direction. Now, we can also, of course, do this for any other point. If I just pick something way up here, we call it sort of, this is a point A, comma B. So I'm just using A as the x coordinate of the point, B as the y coordinate. And if I draw the distance from that point back to the center of the circle, that is also going to be 1, because we are in the unit circle right now. Right, so with that said, we've talked about sort of what it means to be centered at the origin. We've talked about what it means to have a radius of 1, just being that every point is a distance 1 from the center. The last thing we need to talk about is what we can sort of learn by telling that this thing is a circle. If you think back to some of your high school classes, there is one equation that is super important for any study of circles, and that's this one, the equation of a circle. Now, what this is telling us is the x and y coordinates of any point along the perimeter of this circle if you square them, they're going to add up to the radius squared. Now, of course, we're dealing with the unit circle, so this radius is always going to be 1, and 1 squared is just 1. So you'll often see this simplified as just for any point. If I take this AB point, for example, I'll just start substituting things in. The x coordinate is a squared, y coordinate is b squared, the radius squared is 1, as we said. So what you end up with is something like this. And so that's what it sort of means when we say that the unit circle is obviously a circle. So let's do a quick practice problem just to see how some of these principles are used in practice. I'll read it out first. We're told that the point P, which has an x coordinate 3/5 and a y coordinate of b, lies on the unit circle. And then we're told to solve for b. And then I've just put a reminder of what the equation for a circle is down here. So we're told that this thing lies on the unit circle. Therefore, the first thing I'm going to do is to give another attempt at drawing a unit circle. And we're told that the x coordinate is 3/5. So we already know that out here is the point. This is 1 on the x-axis because it's a unit circle. So 3/5 is going to be, about halfway-ish there. So if that's the x coordinate of my point, we're told that P is on the unit circle. So I've just drawn a dotted line up here to intersect with the unit circle. And that is the point P, which, as we know, has an x coordinate of 3/5. Go ahead and label this as 3/5. And then B is the y coordinate. Okay, so the other thing that we know about this is, as I mentioned on the previous slide, any point on the unit circle is going to have a distance of 1 away from the center. So that distance right there is 1. And finally, we know that the equation of a circle should hold for any point on the unit circle. So I'm just going to go ahead and plug in the values of P here. So our x is 3/5 squared. Our y is going to be b squared. And then r squared, as we said, unit circle has radius 1. So this r squared is always just going to be 1. Now I'm going to go ahead and expand out some of these terms. So this first one becomes 9/25. B is just b squared equals 1. I'm going to go ahead and subtract 9/25 from both sides here. So we got b squared equals 1 minus 9/25, 16/25. And then the last step is to just take the square root of everything. So the square root of 16 is 4. The square root of 25, is 5. And so this seems like a reasonable answer for what b is. If I draw over the y coordinate here, b is equal to 4/5. Just looking at this, it looks, looks reasonable. My circle isn't the best drawing in the world, but it seems like this works. Now, there is one part I sort of glanced over here, which is this final step when we go from b squared to b. And here we took a square root. And whenever you take a square root in math, you normally have to consider both the positive and the negative square root of a number. So here, we already said that b equals positive 4/5. Looks like a sort of reasonable answer here. But there's another reasonable answer that puts us exactly the same distance into the negative axis. So somewhere down here, we're being told that b equals minus 4/5 is an equally valid answer to this problem. And so if you just look at this diagram for a moment, you might sort of start to see why b equals minus 4/5 could work. You see, all we were told at the beginning is that the x coordinate was 3/5. There's a second point that has an x coordinate of 3/5 if I go down from the x-axis here on the unit circle. And this point is equally valid. It also has, I'm just going to call it p prime. It also has an x coordinate of 3/5, but now the y coordinate is just negated. And so really, this was a bit of a trick question. There's 2 possible points P, and there's 2 possible values of B. And we'll see this idea come up more in just a little bit. Okay, now that we've learned a little bit about the unit circle, now we're going to go to the trig functions. These are, again, like I said, the bread and butter of trigonometry. And to introduce this, we are going to cheat just a little bit, and we're going to use triangles just to introduce it. But you'll see that by the end of this slide, we're going to totally get rid of the triangles and be back to circles, because that's really what we want to focus on for this lecture. I'm just going to draw some arbitrary point P up here, and just like before, I'm going to label the X and Y coordinates as A and B. This is the unit circle, so we have a radius 1 that drops down like this. Now I'm going to draw one more line here just to indicate where the X coordinate is. Now, if we look at the point P, our X coordinate is A. This distance here is A. And we also notice that this distance up here is the vertical coordinate of the point P, so this is B. Just by the way I've drawn this, you might notice that this angle here is a right angle. And if I give this angle a name, let's call it theta, this suddenly looks like a very standard right triangle from your math class. Now, we normally define sine and cos using this sort of weird mnemonics, but we define it as a ratio of the sides of this triangle. So normally we would have sine of theta. This is sometimes known as the opposite side over the hypotenuse. And so in this case, the opposite side, the side opposite theta, is B. And by the way, don't worry too much if you don't follow this, because again, we're going to scrap triangles completely in just a second. The hypotenuse here is 1. Now, divided by 1 doesn't do anything, so we'll just keep this as B. Cos theta is defined as the adjacent over the hypotenuse, which in this case, the adjacent side is A over 1, which is again just equal to A. Now, you might notice at this point that we have sort of these very nice equations for sine theta and cos theta. If we just forget for a moment about all this stuff that came in between, we have that sine theta is exactly equal to B. And again, forget about all this stuff in between. We have that cos theta is exactly equal to A. If we plug that into our point P over here, we have that equivalently, P equals AB. That's the same as saying P equals cos theta, comma, sine theta. And this is sort of the key realization to shift from the triangle way of thinking to the circle way of thinking. And again, you really want to be thinking in terms of circles for the purposes of quantum computing. Now, I'm going to say for the next little while that we're just going to define cosine and sine as the X and Y coordinates of a point on the unit circle. Now, this is really important, so I'm just going to repeat that one more time. We define cos theta and sine theta as the X and Y coordinates of a point on the unit circle. Notice cos theta, sine theta, we use unit circles, we use XY coordinates. Nowhere here does this definition actually talk at all about triangles. And so this is the definition we're going to try and stick with. We get rid of this sort of idea, triangles, we don't need that right now. All we need is this angle theta, a point on the unit circle, and that gives us our definitions of sine theta and cos theta. Now, there's one more angle here, sorry, one more function here that I haven't mentioned, and that is the tan function. So there is a way of sort of drawing the tan function on the unit circle. We're actually not going to do that right now. It turns out for quantum computing, the best way to think of tan theta is just in terms of a mathematical definition. So you might have seen this before, but tan theta is just defined as the ratio of sine theta and cos theta. So if we draw a point on our unit circle again, let's say P equals AB. What this is saying, recall, is that sine theta is sort of the y coordinate, or b. Cos theta is the x coordinate of our point, or a. And so what tan theta gives us is this quantity, the y coordinate over the x coordinate, or b divided by a. Now it turns out that tan is normally most useful when you use the inverse of this function. So what do we mean by the inverse? It just means that we sort of get rid of the effect of tan on both sides of this equation. So if we get rid of tan on the left side here, we're just left with theta. And if we get rid of tan on the right-hand side, we write this as tan, the little -1, the -1 meaning inverse. So we're taking the inverse tan of sine theta over cos theta. So why is this important? Well, in all of the previous examples I've said, we always had a point P, we always had a line here, and we always had an angle theta. And this is sort of implying that we know what theta is. If we know what theta is, then we can plug it into cos theta and sine theta, and we can figure out what the x and y coordinates of this point are. But what if we flip this around? What if we knew a and b, but we did not know theta? In that case, we could use inverse tan. And so again, you would, if you wanted to find theta, you would write it as theta equals inverse tan. Again, y coordinate over x coordinate. So if you know what b is, you know what a is, then you can go ahead and solve this for some number. This is really the main area where tan is applied within quantum computing. All right, so we've introduced the unit circle, we've introduced sine, cos, tan, and inverse tan. Let's do a really quick review of what we've seen so far. So we started off with a circle, the unit circle. And this circle, we said, had radius 1. So the distance from the origin to any point on the outside was always 1. We drew ourselves a little angle theta here, and then we defined cos theta and sine theta as being the x coordinate and y coordinate of that point on the unit circle. Now, we can actually go ahead and plug in some real values just to see how this would work. For example, if I drew an angle here and I told you that this angle was 30 degrees, then you could immediately go and figure out what the x and y coordinates are. You would just have cos 30 degrees, sine 30 degrees. And I'm sure you've seen the sine and cos buttons on your calculator. You can just go and plug this in. It'll spit out some values, and those are your x and y coordinates. Now, of course, this works elsewhere on the unit circle as well. If I had a line straight out here, as an example, this whole process still works just the same. So let's just suppose that this new angle I've drawn here is like 135 degrees. Same deal. The x and y coordinate are still defined as cosine of theta and sine of theta. So here we have cosine 135 degrees and sine 135 degrees. Same deal. Again, I can go somewhere else completely. I can go kind of in the bottom right of the circle here and draw a line out there. Now, it's worth noting here, it might be tempting to measure your angle like this, but I will point out that we always want to start our angles going up from the x-axis. So we're not going to do that. We're going to measure this angle as going all the way around like this and coming up to meet us. Say this is something like 300 degrees. With these definitions, exact same thing. Hopefully you're starting to see the pattern here. The x coordinate is cos of 300 degrees, and the y coordinate is sine of 300 degrees. Just to kind of hit this point home, we have a quick animation here. What you're seeing in this animation is our point P just moving continuously around the circle, right? So this is the unit circle. Our point P is moving all around the circle. The angle theta here is the same one that I've been drawing. So it starts, you notice, always going up from the x-axis and following the point P around the circle. And then the blue and red dots are the x and y coordinates of the point P as it moves around the circle. And you'll see that those are always equal to cos theta and sine theta. All right, I'll pause briefly here just to answer any questions if people have them.
My mic is on, right? So Corbin, I'll
Yes.
just repeat some of the questions which I found while answering so that you can dwell on them.
Sure.
So one of the question is, Liam McKay, wait, if you only have the angle, how do you find the cos and sine? So.
Yeah, good question for sure. So if you only have the angle, what I'm going to say for now is you just use a calculator, right? So all I've been calling it is I've been calling it cos theta, sine theta. Normally in quantum computing, in this course in particular, you'll almost always be allowed to use a calculator. You can just plug those things in. Now, in the next section of the presentation, we're actually going to talk about some special angles where you can just sort of use some intuition and some visuals to figure out what those angles should be. But for the time being, just say that you can plug it into a calculator and it gives you your answer.
Okay, so another one, I'll just group two questions into one. One is asked by Ansh Gupta and one is anonymous. So they're both concerned about memorization. So they are both saying, so one is saying, do we need to memorize inverse trigonometric values and formulae for the course and application? And the other person is saying, is there any formula to learn the values of sine, cosine, and tan? So basically they're worried that, oh, do I need to know sine 22.5? So you can clarify that maybe.
Right. Yeah, so I really want to not put too much emphasis on memorization here. If there is anything to remember, I would say it's the equation of the circle. And in particular for the unit circle, remember this is always just one. So that's one thing to remember. The other thing to remember is that cos theta and sine theta are defined as the x and y coordinates of a point on the unit circle. So that was our x coordinate and that was our y coordinate. Besides this, there's, as you'll see in just a moment, you can sort of figure everything else out on your own just from these basic facts. As far as the inverse tan that you asked about, again, you will sort of, you'll get a feel for some special angles, which we'll talk about in just a moment. But for the most part, no, you don't need to memorize anything. As long as you have this visual intuition of what the unit circle looks like, if you can keep this picture, essentially, this rotating picture here in your head, that's all you need from this part. Okay, so I think I will charge ahead. So the next topic up is degrees and radians. So this is going to be a little bit of a quicker section. I first want to talk about just some of the motivation for different units of measure. So from my introduction, I'm from Canada. And in Canada, when we measure temperatures, we talk about degrees Celsius. So where I am right now, it's about 5 degrees Celsius. It's kind of chilly outside. But for many of you who are coming from the US, you might be more familiar with a Fahrenheit scale. And so I would translate this, and it turns out that 5 degrees Celsius is roughly, I haven't actually done this conversion, but it's roughly 40 degrees Fahrenheit. And so that might give you a better idea for what the temperature is. But the basic idea here is that both of these values are measuring the same thing. They're both measuring temperature. It's just different ways of expressing certain temperatures. In the exact same vein, radians are just a different way of expressing angles in a circle. In order to talk about radians, though, why don't we first talk very quickly about degrees and why degrees even exist. So degrees, as we mentioned, are a way of measuring an angle. Now, if I go all the way around the circle, you might remember that a circle, a full rotation, is 360 degrees. Now, just from that information, I can determine a bunch of other angles on the circle. So for example, the angle of a semicircle or a half circle here, even if you don't have this memorized, you can just sort of look at this picture and realize that that angle should be half of 360. And so indeed, this is a 180 degree angle. And same thing if we look at the rotation for a quarter of a circle. Again, we just cut 180 degrees in half, we get 90 degrees. And then if I want to go one more level here, I'll just cut this angle in half explicitly. And this last angle here is going to be 45 degrees. So notice all of these different angle measures here, they all come from the fact that a full circle is 360 degrees. And the way that we'll introduce radians is sort of by asking, well, why does that number have to be 360? What's so special about 360? And the answer to that is there isn't really all that much special about 360 degrees. And so instead, we're going to use a more useful definition for what the full circle is. We're just going to define this as 2 pi radians. So if you go all the way around a circle, you've gone 2 pi radians around the circle. Now, this at first glance might look even more complicated than saying 360, but we'll find out in a moment that this is actually a very natural way to think about angles, which is why mathematicians tend to use it so much. Just like with degrees, we can find other angles on the circle just by dividing this full value. So if we wanted a half turn around the circle before we took 360, divided it by 2 to get 180, now we're going to take 2 pi, divide it by 2, and we just get pi. Same thing for the quarter circle. 90 degrees is half of 180. So now for radians, we're going to take half of pi over 2. And then you remember I cut this angle in half again. So we're going to take half of pi over 2 again to get pi over 4. And so it would be good to just sort of look at this, start getting a feeling for what a pi over 2 angle is, what a pi over 4 angle is. But if you ever forget, you can always just go back to the fact that the full circle is 2 pi radians, and then you can just divide it up from there. Now, radians, as you've already noticed from my notation, are sometimes written as rads. This is the same thing, it's just a shorthand notation for it. And sometimes you'll see it just without any units at all. So you'll notice when I drew things over on the side here, every time I wrote a degree value, I had the little degree symbol above it. But when I wrote these radian values, I didn't have anything next to them. So if you ever see an angle measure that has no unit attached to it, you basically just assume that that's radians. The second question I promised we would answer is why radians? So we already had this, reasonable system of using a 360-degree circle to define all of our angles. So why 2 pi? Well, let me just go ahead and draw this similar diagram again. So our full circle was 2 pi radians. And now I'm going to ask you whether this 2 pi value sounds familiar at all. And some of you might be able to recall from math classes that the circumference of a circle, I'm just going to call that c, that's equal to 2 times pi times the radius. Now, again, we are in unit circle land here, so the radius is just 1. I'm going to get rid of that. And so the circumference of this circle is 2 pi, which is the exact same as the angle that we went around to get the full circle. So if I asked you a follow-up question, what's sort of the circumference or the distance around half the circle? Well, you can just look at that and say, if you're asking for halfway around this circle, that's just going to be half of the full circumference. So 2 pi divided by 2, that's just equal to pi. And lo and behold, from the previous slide, what is the angle around half of a circle? The angle around half of a circle is pi radians. And so this is why mathematicians choose this 2 pi value. It's to make it so that all of our radian measures have this very natural connection to the distance around the circle. In fact, I can do this for any arbitrary angle. So if I just draw something here, some angle theta, the distance around the circle for that angle theta, that distance is going to be exactly theta. And so there's no further conversion you have to do here. The last thing I'll touch on is just how you convert from degrees to radians. So if someone gave you, I don't know, some value, say like 225 degrees, and asked you to convert this to radians, all you have to do is multiply by pi over 180. This might be a little bit difficult just to do in your head, but this is actually going to give us 5/4 pi. Now, you could go ahead and memorize this formula. That is totally valid and perfectly fine. But as I said, the way that I like to do this, I just like to remember that the full circle is 2 pi radians. And then if I'm ever asked to find some other angle, I just find out how to divide the circle into that many pieces, and that's how I find out the number of radians. So let's have a quick review of what we talked about with degrees and radians. We started off with the idea that a circle has 360 degrees in it. And we noted that this 360 degrees was kind of just a random number and doesn't end up giving us any natural connections to other parts of math. So instead, we picked a value that does give us some natural connection to the circumference of a circle. And so we called this 2 pi radians instead. Now, radian angles can be found the same way that you work from 360 degrees. Half a circle is just going to be half of 2 pi radians to get pi radians. Quarter of a circle is just a quarter of 2 pi. So that gives us pi over 2 radians, and so on. The final point we touched on was that the reason we picked radians in the first place is if you look at some angle, so I'm just going to look at the angle pi over 2 radians, and you look at the distance around the circle to get to that angle, this distance is exactly pi over 2. And these two will always match. All right, so I'll pause again really quick for any questions that might have come up about radians.
So I haven't seen much about radians, but people are asking about some previous stuff. So one is like,
Sure.
A lot of people are asking about tan and tan inverse.
Okay.
So maybe you can like repeat that part or something. Just tell them that notation about angles.
Yeah, absolutely. So why don't we just go all the way back to our tan and inverse tan slides.
Yeah.
Yeah, so I'll just go over this again. The number one thing to remember about tan for the purposes of quantum computing is really just this definition. Tan theta equals sine theta over cos theta. Again, there is sort of an intuition behind this. I don't tend to like it as much, and so we're just going to stick with this definition. The reason that this definition is useful is primarily for computational reasons, right? So as we sort of mentioned earlier, in most of the slide deck, I've been assuming that we knew theta. And if you know theta, you can go ahead and plug it into cos and sine on your calculator, and that gives you the x and y coordinates of the point on the unit circle. But if you turn that around and ask, what if we knew cos theta and sine theta, or equivalently, what if we knew the x coordinate and y coordinate of P? How would you find out theta? There isn't sort of a natural button for that on your calculator. And so that's where we went and defined this inverse tan formula. And so inverse tan is really only used whenever you have this question of, if I give you the x and y coordinates, I want you to find me the angle. Then all you need to do is go to your calculator, inverse tan function, and write up the y coordinate divided by the x coordinate in the tan function, or inverse tan function, sorry. Press enter, and that will give you back the angle of theta that you have to go around the circle to get to that point. So I totally agree that this tan function is kind of more confusing, certainly, than cos and sine. Cos and sine have this very nice sort of relationship back to x and y coordinates. Tan does not. Tan just has this very mathematical statement where you define it as a ratio. But it turns out to be useful for solving pretty much one specific type of problem, which is when you're given coordinate points and you want to find the angle. That's really all you need to remember for the tan and inverse tan functions.
another thing is a lot of people are bringing in, like since they have seen them in the classes, sec, cosec, and cot, and they're like, oh, talking about them, they're pretty equivalent. You can just make that point maybe.
Yeah. So those things are all certainly interesting, I guess, for various parts of high school math. Don't worry about them at all for quantum computing.
I just want to make you harder that, like it's the same thing, but calculate this, so.
Yeah, it's kind of, I've always found it as just an additional confusing factor. You will, I mean, I've never seen it come up in any of my work. You just need sine, cos, and tan.
Yeah, cool. People are asking, do you need sine A plus B and all that? But I guess you are still to go over identities, right?
Correct. Yeah, I'll just save that for the identities section.
Okay. Cool. Yeah, I can't see any much other stuff, so you can keep going, I guess. I don't know.
Sure, sounds good. Next up, we'll talk a little bit about special angles. So this goes back to one of the questions that was asked earlier. Well, you've been telling us, sine of theta is the y coordinate, but if I tell you that theta equals like 0.215, how does that actually help me? Well, up until now, I've just told you, plug it into a calculator, right? Take out your calculator, hit the sine button, type in 0.215, and it'll give you your answer. But it turns out we can do a little bit better than this. We actually already have the tools we need to figure out the sine and the cos of some special angles. So let's go back to our unit circle here. And let's refresh ourselves on some definitions. First of all, at the very first slide, when we defined the unit circle, we went out to this point here on the x-axis, and we said that we knew what the coordinate points were. We knew that it was a distance 1 away from the origin, and that it had a y coordinate of 0. Furthermore, we went straight up the y-axis at this point, and we said that we know this has a height of 1 and an x coordinate of 0. So this point must be 0, 1. Then, when we introduced the sine and cos functions, we learned that any point on the unit circle is in fact given with its x coordinate as cosine of theta and its y coordinate as sine of theta. That goes for these points too. These points are also on the unit circle. And so these 0, 1, this is going to be equal to cos of some angle and sine of some angle. Likewise, our 1, 0 down here is going to be equal to cos of some angle, sine of some angle. And now we just need to come up with what angle of theta we need to get to these two special points on the unit circle. We'll talk about this one here first. If you imagine just compressing this angle theta down, we would move this arm all the way down until we hit this point right here. Now that point happens when theta is completely squished and theta is 0. So in fact, this point on the x-axis happens when you have an angle of 0. And so we can say that this point is cosine of 0, sine of 0. These two expressions for the point are exactly equal. And so we can just sort of compare the x coordinate to see that the cosine of 0 is 1. And then we can compare the y coordinate to see that the sine of 0 is 0. And just like that, we have our first set of special angles, 0 radians. So whenever theta is 0 radians, we know that the cosine is going to be 1 and the sine is going to be 0. Now, we could do this same exercise for the point straight up on the y-axis. If we let our angle theta go all the way up to 90 degrees, which if you recall is pi over 2 radians, then we know that the x coordinate of that point will be cos of pi over 2, and the y coordinate will be sine of pi over 2. Again, these x coordinates are equal, these y coordinates are equal, and so we know what cos of pi over 2 is. It's just the x coordinate 0, and we know what sine of pi over 2 is. It's just the y coordinate, which is 1. And so here we have our second special angle, pi over 2 radians. Whenever you see that the angle is pi over 2 radians, you automatically know that the cos is 0 and the sine is 1. Let's do one more special angle. If I select a point that's exactly in between the x and y axes, so this is, if you know this notation from math, this distance here is going to be the same as this distance here. That's all those little ticks mean. I'm going to draw a line going all the way back to the origin, and I'm going to ask what this angle is. So we know a 90-degree angle is pi over 2 radians. Half of that is going to be pi over 4 radians. Now, just like I said before, if we label our point here, we know based on the definition of cos and sine that this is going to be cos pi over 4, comma, sine pi over 4. By definition, the cos and sine are the x and y coordinates on the unit circle. Now we can look at the x and y coordinates here. But we actually don't have a good idea of what these are, right? In the previous slide, we sort of used the fact that this is a unit circle to figure out what the coordinates should be. But now the unit circle only tells us this distance here, which is not the x coordinate or the y coordinate. But we can observe, just based on the symmetry here, because I cut this area in between the x and y axes, I cut it perfectly in half. And so the x and y coordinates of this point, at least they're going to be equal. We don't know what they are, but they're going to be the same. So I'm just going to assign a value of a to both of these points. And so we know that this point, which has x and y coordinates of cosine and sine, is going to look something like, oops, sorry, not b, notably. These are both going to be the same value, a. Okay, so this helps a little bit. We know that cosine of pi over 4 is going to be equal to a, and we know that sine of pi over 4 is going to be equal to a. We just need to find a. So how can we do that? Well, we can go back to our trusty companion, the equation for the unit circle. We have that x squared plus y squared equals 1 for any point on the unit circle. Indeed, our point AA over here is on the unit circle, so this should work. I'm going to go ahead and plug in our values here. So A is the x coordinate, the y coordinate is also a. So we end up with 2a squared equals 1. Now this is an equation with one variable, so we can go ahead and solve this. I'm going to divide by 2 on both sides to get a squared equals 1 over 2. And finally, I'll take the square root again. We've seen this before. The square root of 1 is just 1. The square root of 2 is there in the denominator. Now, before we mentioned that you could take the positive or the negative of this, we're not going to worry about that for the time being, since it's pretty clear from this picture that a is positive on both axes. Now, just as sort of a technical note, you will sometimes see people write this 1 over root 2 as root 2 over 2. These are in fact the same, even though they look a little bit different at first glance. And the way you can prove this is just by multiplying right here by root 2 over 2, root 2, sorry. Now notice the numerator and the denominator here are equal. So this whole term is just 1. And so multiplying by 1 doesn't change the value. A square root of a number times a square root of the same number just gives you that number. And then on the top, we have 1 times root 2 gives root 2. So in fact, this 1 over root 2 we got is root 2 over 2, and that is our value of a. Let's go back to our drawing of the unit circle over here. Why did we care about a in the first place? Well, because we knew that a was the x and the y coordinate of our point. And we also know by the definition of sine and cos that cosine is the x coordinate and sine is the y coordinate. We can set these equal, and so we have cos pi over 4 equals a, and we just solved for a, it's root 2 over 2. Same story for the y coordinate. We'll just set the y coordinates equal to each other. So the sine of pi over 4 is equal to a as well, which is root 2 over 2. And so this gives us our last special angle. Our angle is pi over 4 radians. And so I'll just go to the next slide. It has a nice summary of this. And so these are sort of all of the angles that we talked about. We had an angle of 0 radians, an angle of pi over 2 radians, and an angle of pi over 4 radians. And in any of these cases, you can just figure out what the x and y coordinates are on the unit circle. And the x and y coordinates, remember, automatically give you the sine and cos of the angle. So let's do a quick review of how we got here. I will mention as well, by the way, it's not super critical to memorize these formulas. The only reason we're going through this is to give you some intuition of how you can apply these definitions of sine and cos on the unit circle to actually solve some useful equations. In the first case, we said that an angle of 0 corresponded to just sort of flattening this angle theta until the line was perfectly along the x-axis. That point right there is, just from looking at the circle, 1, 0. And so this automatically tells us the cos and the sine of the angle 0. Going up to the y-axis, we have the point 0, 1. We said that this angle here was pi over 2. And so again, the x-coordinate gives us cos of pi over 2. The y-coordinate gives us sine of pi over 2. Finally, we looked at the point right in the middle of these two. We said that the angle there was pi over 4. We noticed that the x and y coordinates would have to be equal because it's sort of right in between. We solved an equation and we found that a, which is the cosine of pi over 4, and also the sine of pi over 4, to be this root 2 over 2 value. All right, so I'll pause there again. Oh, sorry, let everyone look at that for a second. And now we'll do some quick practice problems. Again, just like the previous practice problem, I'll just read it out and then we'll go ahead and solve it together. So we're told that the point Q equals CD. So C is just the x coordinate, D is the y coordinate here. It lies on the unit circle and makes a 45-degree angle with the x-axis. So I'm just gonna, I always like with trig problems, just as a sort of a general tip here, I always like to draw a circle and just start drawing out all of the facts you know. So we're told that this point Q makes a 45-degree angle with the x-axis. And we're told that Q has x coordinate C and y coordinate D, just like that. And that's our point Q. That's all the information we have. Now, how can we translate this to a problem we know how to solve? Well, first step, convert everything into radians. So our 45 degrees becomes pi over 4 radians, just like we saw before. And now we notice that our point Q is on the unit circle. And so the definitions of cosine and sine give us the x and y coordinates of that point. So we're asked to solve for C and D. We know that the two x coordinates must be equal. So C is equal to the cosine pi over 4. Likewise, we know that the two y coordinates must also be equal. And so D is equal to sine of pi over 4. If we quickly hop back and look at the previous slide, we know what the cosine and sine pi over 4 are. We just figured them out. They're root 2 over 2. So we can just write that these are both equal to root 2 over 2. And we finish the question. Let's do a slightly more difficult question. This one looks very similar at first glance, but we'll see that it actually turns out to be a little bit more complicated. So we're told about another point R, which has x coordinate G, y coordinate H. We're told it lies on the unit circle and it makes a 45-degree angle with the y-axis. And so this is the big difference. Previously, we had a 45-degree angle with the x-axis. Now we're told about a 45-degree angle with the y-axis. Again, I'm just writing all the information we know. 45-degree angle with the y-axis. R has x coordinate g, y coordinate h. That's our point R. And now we're told to solve for g and h. Well, just like before, we know from the definition of the unit circle that these x and y coordinates are the cosine of some angle and the sine of some angle. Note, however, and we also know, by the way, 45 degrees, just like before, is pi over 4 radians. It might be tempting to put pi over 4 as the angles in these expressions. But remember what we said about the unit circle. We always start our angles going up from the x-axis. And so really, the angle we want is this thing, whatever it is. It's not pi over 4. So how can we figure this out? Well, we know that this angle here is pi over 4. We also know that this angle is pi over 2. And so if you just add these two things together, you get that the full angle here is 3 pi over 4. Just adding pi over 2 and pi over 4. And so really, the angles that belong here are 3 pi over 4, not pi over 4. Just going to erase these to get them out of our way. Now, unfortunately, we don't know what these angles are right now. This was not one of the special angles we looked at. But because we've drawn it on the unit circle like this, we can still solve this problem. Notice the previous problem we did looked at a point that was 45 degrees, or pi over 4 radians, away from the x-axis. And we solved for this, and we said that the x-coordinate was root 2 over 2, and the y-coordinate also root 2 over 2. Now notice that the y-coordinate of these 2 points is actually the same. And so we know that the y-coordinate of this right point is root 2 over 2. Therefore, h must also be root 2 over 2. G is a little bit different because this x-coordinate here is clearly not the same as the x-coordinate here. But the distance from this x-coordinate to the origin is the same as the distance from the other x-coordinate to the origin. We already solved for this. We know that it's root 2 over 2. And so all we need to do is go in the negative direction. And we have negative root 2 over 2 here. And so G is equal to negative root 2 over 2. So notice that we just did all of this by looking at sort of symmetries of this circle. All right. The one last thing to mention with this is that we had our definition based on the unit circle that gave these coordinates in terms of sine and cos. And so we actually know now, somewhat indirectly, that the sine of 3 pi over 4 is equal to root 2 over 2. And the cosine of 3 pi over 4 is equal to negative root 2 over 2. And so you can actually go ahead and find the sine and cos of a lot of different angles just by looking at how these different symmetries play out on the unit circle. Okay, maybe we can take one question, if there are any.
There was one somewhat interesting one, is that there are different expressions for pi. So some people are like, oh, pi is 3.14. Some people are pi is 22 or something. But then people are like, why is pi 180 degrees? So if you want to mention on like why it's an angle and like stuff like that.
Yeah, no, great questions. So you're absolutely correct. There's a bunch of different representations for pi. You'll always see me write it as just this symbol pi, because there is actually no representation in any sort of simple way that gives a fully accurate definition of pi. So it's always best to just write it as the symbol. As for the question of why pi radians equals 180 degrees, remember that pi radians around the circle, which is, as you mentioned, 180 degrees, corresponds to a circumference around the circle of exactly pi units. And if you don't see that immediately, just remember that the circumference of the entire circle was 2 pi. And so to get the distance around half the circle, you just need to divide that by 2, and you get pi. And so the reason pi radians corresponds to 180 degrees is because you need to go 180 degrees around the circle to get a distance of pi. Okay, I'm going to charge on here just to the last section of my part, which is on some useful trig identities. We're going to introduce these identities by looking at some motivating problems. And so we'll start off with the first one here. You're told that cos of 3 pi over 8 equals this somewhat ugly expression. It's 1/2 root 2 minus root 2, whatever. And then you're told to find sine of the same angle. Now, this 3 pi over 8, that is not one of our special angles at all, so we don't know it. But as with all problems like this, I'm going to start just by drawing some things on the unit circle. So this 3 pi over 8 is somewhere around here, say. That's 3 pi over 8 radians. And we know by the definition of the unit circle that this point is defined as the cosine of 3 pi over 8 and the sine of 3 pi over 8. We already know what the cosine is, and we're being asked to find the sine. Remember, back to the formula of a circle, this is going to be useful for us. X squared plus y squared equals 1. Well, this point here definitely lies on a circle, and so it will satisfy this formula. I'm going to go ahead and start plugging things in. Our x value is cos 3 pi over 8. Squared here, plus the y coordinate is sine of 3 pi over 8. And this is going to be equal to 1. We already know what this cosine value is. It's 1 over 2 square root 2 minus root 2 squared plus sine 3 pi over 8 squared. And now I'm just going to work this out. So if I square this value, I get 1 over 4 times 2 minus root 2. And this value here is actually what we're looking for. Now, you'll sometimes see people write this with the 2. They'll just bring it down on top of the sign. It means the exact same thing. It just saves us from writing one pair of brackets. And now I'm just going to do some multiplication here. So if I multiply the whole thing through by 4, I'm going to get 4 sine squared 3 pi over 8 plus 2 minus root 2 equals 1. Now I'll bring all of that over to the other side. And so we get sine squared 3 pi over 8 is equal to, so if we have 1, we subtract 2 from both sides, we get minus 1, add root 2. And then we're going to divide this whole thing by 4. 1 over 4. Okay, and then I'll go ahead and take the square root of both sides. And I'm not going to bother doing much here. 1 over 4 square root of that is 1 over 2. And then we just take the square root of this whole expression here. And just like that, we have found the sine of a very strange angle. Again, all we're using here is the fact that sine and cos are the x and y coordinates on the unit circle. Now, this whole thing can be summarized as something called the Pythagorean identity, which I accidentally wrote over here. You'll note that this 3 pi over 8, I just chose that kind of randomly, right? This works for any angle theta. And so because any angle theta is going to give you a point on the unit circle, we can say that the cosine squared of theta plus the sine squared of theta is always going to be 1. And you'll notice that this comes up fairly frequently and turns out to be very useful. Okay, next up is negative angles. This is a fairly quick example. So before we had looked at angles like this, that were, pi over 4. Now we're just going to go in the opposite direction. So negative pi over 4 puts us down here. So from our previous slides, we know the cosine and the sine of pi over 4. Those were some of our special angles. And so we know that this point up here is going to be root 2 over 2 over 2. And again, sort of using a similar symmetry trick from what we used before, we actually know what the coordinates of this should be. The x coordinate is going to be the same, and the y coordinate has just been flipped. Just like before again, our negative angles are exactly the cosine and the sine, the cosine and sine of our negative angle are exactly these x and y coordinates. So this is just another example of how you can sort of use the unit circle to solve problems like this. Oops, again, I wrote over my own slide here. So the negative angle theorems, these are just the equation form of them. You don't really have to memorize this. You can always just look at it on the unit circle to figure it out. All right, final identity.
Hey, Corbin, this is Rachel.
Yeah.
I just want to jump in with a time check that it's 11:07.
All right, cool, thank you. So I'll just do a more quick sketch of this, this problem here. Remember from before, we solved for what the angle was as 3 pi over 8. That was when we talked about the Pythagorean identity. Now we're being asked to find the sine of 7 pi over 8, which is an angle that's way out here. Now, I'll leave it as an exercise to sort of think about how you might take the coordinates of this point, which we already found in the previous slide, and convert them to the coordinates of this point. You can do it just by sort of looking at the symmetries of the circle, and I'll leave that as an exercise. What you should end up with is something that looks like this. This is a bit of a hint for how to do this problem, is that 7 pi over 8 is a pi over 2 rotation away from 3 pi over 8. Again, you don't really have to memorize these formulas. You just know that you can look at the unit circle and figure these things out. All right, really quick review before we finish up. We talked about the Pythagorean identity, which just comes from the equation for the unit circle, x squared plus y squared equals 1. And then we talked a little bit about negative angles and rotations, both of which you can see by looking at symmetries on the unit circle. I'll emphasize again that I'm just providing these equations sort of for completeness. You definitely don't have to memorize them. As long as you understand how to draw the unit circle and how to sort of work with it in that sense, you will be good to go for anything that's covered in this course. Okay, so I'll pause here for any final questions before we take a quick break.
Basically, it's like 11:10, so I don't know if I can speak anything. Questions, I actually lost track a little bit in the last one. So yeah, I mean, a lot of people are worried about memorization and stuff. I think you have already clarified that part. Yeah, a lot of people, is there formula for sine and cos? I mean,
yeah, not in general. So the way that you figure out these sine and cosines is often just by looking at the unit circle, and
Yeah.
all the things that we went over today is.
And a lot of people are concerned about the signs of, sorry, not the signs, but the notations, like why you write 2 over square root 2 rather than 1 over square root 2. They are the same. And then a lot of people are confused about calculations. You can go back to this presentation, which will be posted on Canvas, and you can go through it slowly, and I think it will be fine. Like all the things are accurate, I can I can certify. So
Cool. All right. So we will take a quick break then. And I think we'll take maybe just a quicker break, 2 or 3 minutes here. And then when we come back, Rahul will start his part of the presentation.
Y is perpendicular to x. So this is your axis at pi by 2. You drop a perpendicular there, and this length is going to be r sine theta. So this is how you convert between sine land and Cartesian land, right? Okay, cool. So any questions, Corbin, on this section? Like, are people like just saying stuff here, or?
So far, it seems that we're good. People are sort of clarifying some of the exercises from the last section.
Okay, yeah. So, so anyway, so this, for example, is an exercise for you, and I would say homework, because as I said, we won't be doing it in real time. But let's say your mom tells you that your sock is in 3 and 4, but now you are fashionable and in a different land, sign land, and you want to convert it into your language, r and theta. So given this sock at 3 and 4, could you tell me what is r and theta? So just write it down if you have notebooks. I will post this. So this will be a homework. So please try to figure it out. If you can't figure it out, Piazza is always there. So let's move on. So why are we concerning ourselves? So a lot of people are asking that, why do we need trigonometry? Why do we need, all these unit circle and stuff? So let me give you some examples. So vectors. Vectors are something which will be defined in the lecture, and you will come across them a lot, so I won't be defining them. But if you have 2 vectors and you want any sort of operation between them, you want to multiply them, you want to add them, you want to subtract them, what is really useful is to get their components, like we were doing here. So this cos theta and sin theta as components of in this case, it's a point, which is also a vector. But in any general case, if you have a vector, then getting components is really useful to do all these sorts of operations. That's why it's important. And then in the first lecture, I guess you were taught about these cats, these Schrodinger's cat, I guess. So quantum mechanical states are also actually vectors. It's in a different space called Hilbert space, which I will not talk about, but you can look it up if you are interested. But they are vectors. Now, so quantum mechanical states are vector. If you're doing quantum computation, you are going to perform operations on these quantum states, right? That's the definition of computation. You take something, you manipulate it. So to manipulate these states, you will be actually rotating these states around. So that's why knowing trigonometry to figure out what rotation to do, and if you rotate something, what happens, that's why sine theta and cos theta are important. For example, I'll just, so this is a living cat. This is a dead cat. So if I have a cat whose state is given here in the middle, what do you think it will be? So I'll give you 10 seconds to think, and I think you have seen this in the lecture. So okay, so to find this out, right, what we do is what Corbin taught us is that we take a projection here. Actually, Corbin taught us, and I also mentioned the r cos theta and r sin theta part. So you take the projections here. So a living cat, when projected onto this state, is going to be a living cat, I'll just say L over square root 2, which is, let me write it even more pedantically. So it's a living cat, and then cosine of pi over 4. And then if you project a dead cat to this direction, then you have a dead cat, and then cosine of pi over 4. And we have learned what cosine of pi over 4 is. It's 1 over root 2. So what you have is a living cat over root 2 and a dead cat over root 2, which is, I'm hoping people are shouting the answer out in their chats, but this is a Schrodinger's cat. So a Schrodinger's cat is a cat which is both alive and dead at the same time. And as I said, this is just an operation of rotation of a living cat by pi over 4 in Hilbert space, or a dead cat. So, well, cat, as I said, cat is not a real quantum object, but if you have a quantum object on which you are going to perform quantum computation, these kind of rotations will be really useful. Okay, and then you are going to learn about complex numbers. I'm not going to talk about them, but second lecture talks about them, I think. And once you learn about complex number, you will realize that knowing this sine and cosine and how they multiply and how they work with each other, you will get much more comfortable with complex number in something known as a polar form. And polar form is basically our sign line 1a. So that's what. So that's why polar forms are useful. Okay, I would stop for questions if Corbin has any like super important ones. Otherwise, just take a break, and maybe after 10 seconds, I'll start another one. So Corbin, do we have any questions?
So actually the question I was just about to ask is people are asking sort of if Cartesian world is, or you call the rectangular world a Cartesian plane,
Yes.
what are these terms about polar and what exactly is Sineland? It looks like you're about to talk about that though.
Yeah, I mean, okay. So polar is, as I said, so as you can see in this image, actually, Cartesian is mostly about, you're talking about like lines in terms of square grids, because x and y coordinates of a point, if you have to project them to x and y axis, which are rectangular axis. Now, if you look at a polar axis, the polar axis are a set of circles. You see, like this circle, this circle, this circle. So all the points are assumed to lie on a circle, and you draw the circle, and then the radius of that circle gives you r coordinate, and then the angle of the point, angle of the line you have drawn from the zero angle gives you the theta coordinate. So that's why this is a more rounded, you know, like this is a polar bear and this is a Cartesian bear. So it's just so points can be represented in both systems. Polar is sometimes useful if you are thinking about circles and rotation. Cartesians are useful if you are thinking about adding lines and stuff like that. So it's more natural. You can do operations in both of them. One might be easier than other sometimes. So if that was the overarching theme, I will just go ahead. And even in the previous section, people were asking what is a block sphere. So this was only 2D. So now we have advanced from 2D to 3D. So x and y plane, the 2D is here. And now we have added a third dimension, the z-axis. So now we are in 3 dimensions in Sineland. And I start with something called a block sphere. And if you don't get the name, don't worry. This is going to be like your basis in quantum mechanics. You will see it like a lot. And lectures will cover it, homework will cover it, labs will cover it. No worries if you don't get anything here. So quantum states, as I said, they are vectors, and these vectors are represented on a unit sphere, which is known as a block sphere. And any computations you will do, the logic gates in quantum computation you will apply, they will basically move this vector around. So that's why it's sometimes important to look at coordinates on a sphere as well. So we have learned how to represent on a plane. Let's see how to represent on a sphere. So you can already see that now you need 2 angles. So I think this was a question that came up in your section as well, Corbin, but I just told them to wait till mine. So basically now if you want to specify the location of a sock in 3D, where, you know, it's not lying on the floor, but it's maybe in some cabinet or something, right? In your room. So you need to say x and y coordinate and also the z coordinate. But sometimes it's easier to refer to spherical coordinates. So you just give the distance, like in polar coordinates r, and then you give 2 angles rather than 1 angle. So 1 angle is from the vertical, the z-axis, and then the other angle is basically from one of the axes in the plane. So from x-axis in the plane. So that gives you 3 coordinates, r, theta, which is from vertical, and phi, which is from horizontal. But again, as I said, you want to be able to convert between this notation and the Cartesian notation to be able to communicate easily. So what is Z coordinate here? So if you remember this diagram, like again, Corbin drew it in a different way, but again, it's the same thing. You have this R, you take a projection. So projection is a word which will be used a lot. So by projection, I just mean that you have a distance and you know what angle that distance is at. So once you go where the angle is, if you drop a perpendicular and then look at this length, this is called a projection. So you take the projection of this distance. So what will be Z? Again, if you have followed Corbin, you would know that Z is just cosine theta, but since it's not a unit circle, there is R. So it's R cosine theta. Then what is X? Now X is not that simple here, right? Because once you drop this projection, so this is, so the projection along the angle is called theta, and the projection which is not along the angle, the complement of that projection is always sine theta. So, but you can see that this is still not on our x-axis, right? We have fallen onto the ground on the plane, but it's still not along one of our axes. So what we do, we drop again a projection. So now there are two things. So one is you drop on the ground. So that is going to be, I'll give you 5 seconds. Okay, so this is going to be r sine theta. Let me write it out. This is r sine theta. And then if you go here, then this is going to be r sine theta, and then projection along the angle. So this is going to be cosine phi. So this will be your x component. And what about y component? I will leave you to figure it out. This is your r sine theta. Now you are taking a projection, not along the angle, so complementary of that projection. So that will be sine phi. So these are the relations in Cartesian coordinates for a point r theta phi in spherical coordinates. Using these relations, you can go between spherical and Cartesian easily if needed. So, and watch out, mathematicians are usually friendly with us, but in this case, they somehow use a different notation. So if you look at math textbooks or Wikipedia on a math article, they would call this angle phi and this angle theta. So this is just to let you know, but we are physicists. I hope most of us are. Actually, not all of us are, sorry. I should respect everyone. So yeah, so mathematicians use a different convention, but just know that no matter what you call these angles, once you know these angles, you can always find x, y, and z. Okay. So again, this is an exercise, but I will leave it as homework. So just note it, write it down if you have a notebook, or again, this will be on Canvas. So if you know r, theta, and phi, you are in sign land, and now you are speaking a foreign language. You have r, theta, and phi on a sphere, and then your Cartesian friends comes and he's like, oh, I need to borrow a sock. He's like, oh, it's at 2 pi over 4, pi over 4. He's like, what the hell are you talking about, man? Like, I only know x, y, and z. So then can you convert it for him, for your friend? So that's the question. I have the answer here. I'm not going to reveal it, but it's a homework problem. Okay. Any questions here, Corbin?
I don't think so. I've been answering a couple, and so
Yeah.
I will get to all the questions here, or some of the questions here eventually.
Yeah.
But I think you can keep going.
So I don't want to overextend on time. We have 11:30. I don't know if we can ask people if they want to stick around for like 5 more minutes, but I think 5-minute overextension is fine. I mean, even in our colleges. So is it okay, Rachel, or that's the last part? Is Rachel here? I don't know. Okay, I will continue, but it will finish soon. So, okay, so what about waves, right? So the point is with Zoom, I have something on my slide and I can't see what my title of my slide is, unfortunately. Okay, I think it just says Signland 2, right? So we have talked about coordinate system. Let's talk something away from coordinate system, right? You have learned about sine and cosine only in terms of coordinates mostly. But another very important thing where waves come up is actually, sorry, where sine comes up is waves. But why do we talk about waves in quantum mechanics, right? Wave is like in an ocean. Like, what are you going to build a quantum computer out of ocean? Probably not, right? But it turns out, again, this is just an introduction. In lectures, there will be like 3 lectures on one simple topic. So don't worry about it if you don't get anything here. This is just to introduce and tell you that, you know, in quantum mechanics, we have waves. That's all. So there was a French physicist, Louis de Broglie. So Louis de Broglie gave a very revolutionary statement. He said, a particle moving with a momentum p has a wavelength. So if you don't know momentum, it's fine. Basically, any moving particle has a wavelength. That's what this guy said. So, and he gave an expression as well to find that wavelength. He said, lambda, the wavelength, is equal to, I'll talk about what a wavelength is actually, but it's something to do with wave. So that's what he said, that anything moving must be a wave. And how do you find out the wavelength? Wavelength is basically, yeah, I'll go over what a wavelength is. But so the expression for wavelength is some constant h, which is called Planck's constant, divided over p, which is momentum. If you don't know momentum, p is just mass times the velocity, the speed of the particle. So you can find out the wavelength for any moving particle using this expression. So what is a wavelength? So wavelength, you know, this is a wave, right? It's like a wavy thing. So wavelength is you start from a point and then go back to the same point. So this will be called lambda. This is one wavelength. So this is a characteristic, right? If something has a smaller wavelength, it's varying really fast. If something has a large wavelength, then it's going really slowly, right? So, okay. So, and then the question arises, if any particle moving is a wave, then why don't we see everything around us like a wave? So that's an important question. So let's just take a golf ball, for example. And just to make maths easy, I will just say that V is just 1 meter over second. Now you take this, you calculate lambda. Again, these slides will be available. You can take it as a homework, although it's not a big deal. You know, you just take this number and multiply these numbers and divide it by this number. So this is the wavelength you get. This is the point I want to make, that for everyday objects, the chair you are sitting on, the fan probably running in your houses, and you will see that the lambda for any of them is really, really tiny. Like this is like a really small number. Like your hair width is 10 to the minus 4 meters. So you see, it's like the hair on your head. Then then you go on live on your hair. Then there is another hair on your hair, and you know you can keep doing this. And you know it's a really tiny number. That's what I'm trying to say. That it's something you can't see, and that is why everyday objects around us do not appear to be wavy. Now let's talk about something which we use in quantum computation, about, let's say, an electron, right? An electron is very tiny, so its mass is very small. And this is quite a high speed, but as you learn more physics, again, this will be covered in lectures, you will realize that electrons kind of move fast. So if you take these numbers and try to find out lambda again, you will find that now lambda is 10 to the minus 10 meters. Now this is again a very small number, but it is something which is size of an atom. And if you follow science, and you know, you probably realize that there are technologies to see an atom. And in my PhD, this is probably the best thing I ever did, is that I imaged something, and these are actually real atoms. And the wave you are seeing is actually a real wave. And you can see that this is the scale 2 nanometers, which is 10 to the minus 9 meters, and 10 to the 10 is just 10 times smaller. So all these fringes you see are basically, you throw a stone in a pond, you see ripples. These are ripples of electrons. So you are like, I have just shown you an electron wave. So this is just to say that, you know, waves occur in quantum mechanics. Okay, waves occur, but what do they have to do with sign? And I'll be done in like a couple of minutes. So sign, so as Corbin talked about unit circle, you must have realized that once you go around the circle and come back to some point, then it's just same as being on that point on the first place. So all the trigonometrical functions, sine, cosine, tan, are periodic. By periodic, I mean that you add a constant to their argument and then they remain unchanged. In terms of sine and cosine, it's easy to see. you have a circle. If this is your theta, now you go around 2 pi and then come back to this theta, then you are at the same point, right? X and Y coordinates are the same. So as Corbin very excellently explained. So these are periodic. And you remember what else is periodic? You see this? It's just moving between two values, let's say +1 and -1. So waves are also periodic. So you can express waves as a sine function. And when we do that, we usually have some parameters. And we'll quickly go over these parameters in a live, nice web app, and then we are done. So what are these parameters? So this is your familiar sine function, hopefully, after all this introduction. But now its argument, rather than just simply being a number theta, it has a lot of stuff in it. So let's see. So A is the amplitude, how big a wave is. Like a wave in your coffee cup is much smaller than wave in an ocean. So A will be larger for ocean, smaller for your teacup. And then K is something known as a wave vector, or you can relate it to what is known as frequency, or how often things repeat. So for example, let's say what's fast. So sorry, I can't think of examples right now. But so something is really slow, like an earthworm is moving. You count like number of steps of earthworm. That will have a very low wave vector if you plot how an earthworm is moving. But if you're plotting how a cheetah is moving, for example, or a leopard is moving, it's moving really fast. So if you plot the position of leopard, then you will see that it varies much more faster. So if you represent both of them by waves, the wave vector for earthworm will be very small, and the wave vector for cheetah will be very large. And phase is basically where the starting point of your wave is. So if you set phi to be 0, you just have sine kx. So x starts at 0. Now you can set phi to some non-zero value, and then that just basically means that your wave starts at a non-zero value. So let us just quickly see them. I said 2 minutes, but yeah, I'm definitely finishing on 11:40. So I just want to show these things on what is known as a GeoGebra, and also introduce you to GeoGebra. You should use them in your homeworks and classes and just have fun here. So GeoGebra is a website, just Google it, and you can plot anything. So let me just plot some function equals sine. By the way, Corbin introduced me to this, so thanks to him. So you see, this is a sine wave. It's going between plus and -1. And then let's plot a wave with all the parameters. So here, let's plot, like, let's give it an amplitude, let's give it a wave number, and let's give it a phase, which I'll just call P. And then the total wave for us was, let's call it G of x equals A times sine K x plus P. Right, so this is in orange. I wish I could change the color. The orange is not very obvious on red. But anyways, so let us see how these things affect a wave. So if you increase amplitude, wave becomes big. Reduce amplitude, wave becomes small. So this is the amplitude. And the K, so you increase K, wave becomes faster, moving up and down really fast. So frequency increases. You reduce K, becomes really slow, varies really slowly. So now you have learned about A and K. Let me just make them as same as I can. Okay, and then the phase. So phase, when it is 0, you will see that it lies on top of our sine wave, roughly. Sorry, so yeah, ignore that. I made a mistake. So basically, I'm just saying that if you change the phase, you just see that the wave is shifting. So the 0 of the wave, the origin of the wave is changing. So those are the 3 numbers which control a wave. So if you know these 3 numbers, you can tell how a wave looks like, how big it is from amplitude, how fast it is from wave number, and where it starts from phase. So that's about it for waves. So yeah, just wanted to introduce you to waves. So that's all done, and goodbye. And we have a waving bear, and sorry about delays. If you have questions, post them on Piazza, or Corbin can tell me if there are some outstanding questions, but we are done here.
Maybe just one general question that came up is, do we need the graphs of sine and cosine, and sort of to understand more of what you're just doing there with GeoGebra? Does that come up a lot in quantum computing?
It's kind of cool to play around with it. So by wave, yeah, I mean, I would say, yeah, it's good to be familiar with waves. You don't need it now and you don't need it from us. The point is that it will be covered in the lecture. So just don't worry. Like there will be lectures, there will be homeworks. We will take you through that. So yeah, so you need them, but it will be given to you. You don't need it as a prerequisite. If nothing
Cool.
if nothing super important, we'll probably quickly eat something and come back at 12 to do the parallel. Or we can do a
Rachel,
parallel. Yeah.